Welcome to a brand new episode of the fourth season of Zeroing In, the Science Podcast. Today, we are in conversation with Professor Sujatha Ramdorai, a magnificent number theorist. She is the first ever Indian to receive the prestigious ICTP Ramanujan Prize. Professor Ramdorai has made seminal contributions to the field of algebraic theory, of which the most remarkable is her work on formulation of non-commutative version of the main conjecture of Iwasawa theory. Professor Ramdorai completed her BSc in mathematics at St. Joseph's College, Bangalore, and finished her MSc from Annamalai University. Following this, she went on to pursue her PhD from TIFR, where her dissertation was With Groups of Real Surfaces and Real Geometry, and continued working there for a bit longer. Currently, she holds the position of Professor and Canada Research Chair at the University of British Columbia in Canada. In our conversation with Professor Ramdorai, we tried to scratch the surface of the fascinating immense bulk of algebraic theory, while also discussing in depth about perceptions of mathematics in general and the related pedagogical ideas. This conversation opens with what can be called an overview of Professor Ramdorai's rich and expanse research work through the years.
So I started out with algebra. You can think of it as equations, but you see, that's the problem with mathematics. It's not unidimensional. You might be working in a certain subject, but it always has connections to other areas, both within mathematics and also outside of mathematics. So my PhD was in an area called quadratic forms, which is basically the study of, equations in any number of variables. Let's say n. N can be anything from 2. N greater than or equal to 2, and then you want to study solutions of equations of the form a1 x1 squared plus a2 x2 squared plus a3 x3 squared plus so on up to an xn squared, right? You want to understand these equations equals c, say. Now all these coefficients a1, a2, an, c, all of these, you can think of them as being in some field. For instance, you can take the rational numbers. They're not very interesting when you start with complex numbers, because complex numbers, you know that these have solutions and so on. But the moment you come to real numbers, so for instance, take the simplest case, you take x squared plus y squared equals 0. We know that the only solution it can have is when both x and y are 0. So it can never, or if you put -1 on the other side, so it will become x squared plus y squared equals -1. Or if you bring the -1 to this side, then it will become x squared plus y squared plus 1 equals 0. And we know that this will have no solution over the real numbers. But as soon as you go to the complex numbers, it has solutions. And then you can ask, what about, take, let's say, 2x1 squared plus 3x2 squared minus 4 equals 0. And then you can ask, what kind of solutions does it have over the rational numbers? And then, this is typical of mathematics. You don't stick to familiar areas. You always move out of your comfort zone. So you don't just stick to rational numbers or real numbers or complex numbers. These are all what come under fields, right? These are fields. So you want to study such equations over arbitrary fields. And there are lots of fields which are of interest, which have connections to algebraic geometry and so on. So you try to study the equations. When does such an equation, over what kind of fields can you say something more about the solutions of such equations? And this basically this is called quadratic because you see that it's a homogeneous equation. Every variable x1, x2, xn, these are all occurring to power 2. So that's why it's homogeneous. And then you say quadratic because they're all occurring to power 2. And so studying such equations from the algebraic geometric point of view, you want to understand their solutions, then that takes a different tack. Then you give it, actually, it becomes what you call a curve. If it is in two variables in, let's take the simplest example. For instance, you take x squared plus y squared equals 1. So we know that this is a circle. So you think of it as a curve. So in two variables, it has more structure. But then again, mathematicians move out of their comfort zone. You don't want to stick to two variables. You move to arbitrary number of variables. And then you ask, when the solutions exist over a field, what kind of structure does it have, and so on. So this is basically the study of quadratic forms, and they have a lot of geometry, and studying them over the rational numbers it was very important, and it has connections to physics, everything. But of course, like everything, when mathematicians do something, they don't do it just because they feel that it'll have connections to physics or connections to some other area. They do it out of curiosity, sheer curiosity. So this is a subject which is very old. In fact, it goes back, if you ask for integer solutions. So if you ask for solutions for such equations where all the variables you only want to plug in integer values, this goes back to Diophantus. So this is called Diophantine equations. And today this goes under the name of quadratic forms, and that's a very rich area by itself with connections to geometry, connections to physics, connections to number theory. So I started out in that area, and then later, past my PhD, since it has natural connections with number theory, I moved to number theory. And then from number theory, the typical example, everybody knows Fermat's theorem, Fermat's last theorem question. We gave this example, right? Pythagoras, x squared plus y squared equals 1. You can think of it as a special case of Pythagoras theorem. Or more generally, you take x squared plus y squared equals z squared. And then we know that this is an identity satisfied by right angle triangles, Pythagoras theorem. And then we know that it has infinitely many solutions, 3, 4, 5, and so on, all these Pythagorean triples. But then you ask the question, what happens if I go from 2 to 3? So for instance, suppose you still stick to 3 variables, x, y, and z, but now you're asking for solutions x cubed plus y cubed equals z cubed. How many integer solutions does it have? Or how many rational solutions does it have? Rational numbers, solutions in the rational numbers. Because once it has a solution over rational numbers, you can clear the denominators and get integer solutions. So it doesn't matter if you work with rational numbers, or you can ask x to the power 4 plus y to the power 4 equals z to the power 4. How many solutions does that have? And suddenly the whole world changes. For n equals 2, you know that it has infinitely many solutions. But from n equals 3 onwards, of course, there's this famous quotation of Fermat, who said this can only have finitely many solutions, and those are the obvious ones. Unless one of them is 0, x, y, z, the product should be 0. These are the only possible solutions. And he said, I found a marvelous solution for this, but unfortunately, the margins are too small for me to write it down. And then for 350 years, mathematicians were on the hunt to second guess what Fermat's solution would have been. And eventually, they reached the conclusion that he must have made a mistake. And today, I think we understand quite well the kind of trap that one can fall into in coming to a solution. But he was correct. His intuition was right, that there can only be finitely many solutions. But it took 350 years to prove that Fermat was right, but the proof that he gave was wrong, or the proof that he had in mind was wrong. And so this is typical of mathematics. You second guess. And like I tell my physicist friends, physicists are always opening the door and trying to explain why they see what they see. There's a door open and they're trying to explain why you see what you see. Whereas mathematicians always predict what's behind a closed door. And then the physicist opens it and says, wow, you were right. And now let me try to explain why you were right. So this led to the development of algebraic number theory and various tools to understand, or tools towards providing a proof of Fermat's theorem. And one such area which developed is, you take field of rational numbers. Then we all study equations. Like, for instance, we know that the rational numbers is contained inside the real numbers is contained inside the complex numbers. These are all fields. But the distance from Q to R, from the rational numbers to the real numbers, in field theoretic language, it's very large. Meaning there are actually real numbers. For instance, you take pi, or you take e, the natural logarithm e. Those have the property that they are never solutions of equations whose coefficients are over rational numbers. Right? So you can take any equation whose coefficients are rational numbers in one variable. So let's take x to the power n plus a1 x to the power n minus 1 plus so on up to an. And any solution of this is what's called an algebraic number, where all the coefficients ai are in the rationals. And it took a long time to understand that within real numbers, of course, this is a long time in the sense, goes back a very, very long time. Maybe people knew it early millennia, 2000 years back and so on. But To formalize it, it took more than, all this was formalized in the last 300-400 years. So these are what we call finite extensions of the rational numbers. So which means you have Q and you're looking for fields which contain the field of rational numbers, and such that these fields can be generated over Q as a vector space by finitely many elements, right? Linear algebra, when you think of a bigger field containing a smaller field, then that bigger field actually becomes a vector space over the smaller field. And then once you are in vector space, you can talk about dimension. How many linearly independent elements does it take to generate this bigger field? And if it only requires finitely many elements, so for example, the simplest example is going from real numbers to complex numbers. So complex numbers can be generated using the real numbers and just this square root of -1, because every complex number is of the form a plus bi, where a and b are real numbers. And now if you allow finitely many such elements, so that any element can be written as a1, e1 plus a2, e2, where the ai's are in the smaller field and the ei's are in the bigger field, then this means that you can reach the bigger field by just finitely many props, by just finitely many elements. And like I said, going from the real numbers to the complex numbers is like that, but going from Q to R, from the rational numbers which are contained inside the real numbers, you can never cover all the real numbers, starting from the complex numbers and adding a few elements in the sense of vector spaces. Okay. More, it's worse. There are actually real numbers which don't satisfy any equation over the complex numbers, which are not solutions of any equation whose coefficients are in the complex numbers, equation in one variable. So such numbers are called transcendental numbers. But on the other hand, there are lots of numbers which satisfy equations over the complex numbers. For instance, you can take 1 plus square root of 3 or square root of 5. Square root of 5 satisfies x squared plus 5 equals 0, right? So such elements are called algebraic numbers. One of the important goals was to study what can we say. And this is very important because when you want to solve equations with coefficients in the complex numbers, then you want to understand, we know abstract mathematics tells us that any equation can be solved. And you know that if it's an equation of degree n in one variable, it has n solutions when you count it with multiplicity. But the point is, all these solutions lie in what is called the algebraic closure of this field, Q bar. Now, how far is Q bar from Q? And usually to measure that, any master's student who's studying mathematics will know in the study of equations, Abel and Galois, they came up with this fantastic theory called Galois theory, which allows you to study equations over fields, solutions of equations over fields, and also how to solve them, and why some equations cannot be solved just using the coefficients. So for instance, if you take a degree 2 polynomial over any field, we know this is something we learn in high school, ax squared plus bx plus c equals 0. You know that the roots are minus b plus or minus square root of b squared minus 4ac divided by 2a. So you can express the roots, the solutions for the equation purely in terms of the coefficients. And you can do this even for degree 3 equations, degree 4 equations, but beyond that it stops. And Galois theory explains why it stops. But abstractly, you know that all these solutions lie in a big field which is called the algebraic closure of the rationals. But how far is this algebraic closure from Q? What is the degree? We know that it's infinite, but can we still describe it? And the only way to measure this is what's called the Galois group, which is a group associated to any field. Take any field, you can define what's called the algebraic closure of that field. The algebraic closure is one big field which contains the field that you're starting with, where all solutions of all equations over that field that you're starting with can be found. But how far do you have to go? For instance, from the real numbers to the complex numbers, you don't have to go far. You just have to add square root of -1, and then any equation over the real numbers has to find all its solutions in the complex numbers. But for any arbitrary field, it's not known. Abstractly, you know that such a field exists, but how far do you have to go? That's an open question. And especially so for Q, and it's really galling because the field of rational numbers is something that's been known to humanity for a very long time. But yet you don't understand the algebraic closure of Q, and you don't understand this Galois group. How far do you have to go to get to the algebraic closure? So algebraic number theory arose because of that. Again, it has fascinating connections with algebra, with geometry, and other areas in mathematics. And one such question, if you want to understand this algebraic closure, you can say, okay, that's maybe too far, but can I understand other bigger fields which contain the rational numbers? So typically, let's start with 1. You know, 1 square root of 1 is negative, plus or minus 1. These are there in every field. Every field has plus or minus 1. But then let's take cube root of 1. That is, you want to look for the solutions of x to the power 3 minus 1. Or let's stick to a prime number because it's easier to understand things prime by prime. So let's fix a prime number p, and then let's look at x to the power p minus 1, or x to the power p squared minus 1, x to the power p cubed minus 1. So these are all, we know that it exists, and they exist in the complex numbers. For instance, if you start with q. So you attach all these roots, so then these give you bigger fields which contain the field of rational numbers. So now, how do you understand these bigger fields? So typically you understand these bigger fields by giving them more structure and then giving invariants to these fields. And Iwasawa theory began in the 1960s. So associated to each such group field is a very important invariant called the class group, which is actually a group which is a finite group. And Iwasawa started his study to understand these field extensions by trying to understand the class group of these fields. And how do they grow? So you have, let's typically start with, let's say, p equals 3 or 5. So then you have the cube root of unity. Then you have the 3 squared, which is the 9th root of unity, 27th root of unity, 81st root of unity. Or similarly, if you take p equals 5, you start with the 5th root of unity, 25th root of unity, 125th root of unity, 625th root of unity, and so on. So these all give you field extensions of Q. And then you want to study the class numbers, which are invariants associated to these fields. And then you want to measure how this class group is growing. And that was the way Iwasawa started his study. But then it soon branched out to a whole different field called Iwasawa theory, which now I cannot go deeper into that because it gets very technical even to explain. But the inspiration was this simple question. You want to understand bigger and bigger fields. And then they found that many such techniques he developed could also contribute in understanding other field extensions or other arithmetic, groups coming from geometry or arithmetic and so on. So that today is called Iwasawa theory. And interestingly, I want to tie it up to Fermat's last theorem because Iwasawa theory was one of the tools. Initially, it was used, but later it was subsumed. But it was always hoped, and it was correct, some insights from Iwasawa theory went into the eventual solution of Fermat's last theorem. So I think this is all I can say about the area that I'm working in.
I mean, that sounds quite fascinating, and I like how you've started from the fundamentals and we've built it on to something huge that you're working on. So, actually, like when we talk about mathematics in general, it's there, and you know that everything can be explained in the language of maths. Like you said, like it's behind a closed door, and you try to guess what's out there without even seeing it. So there's always a way math explains things. So in your perspective, this can be a little abstract question, but would you call mathematics an invention or a discovery?
Part of it is discovery, but to explain the discovery, when you discover something, you see something, right?
Yeah.
But you would still try to understand why it is what you're seeing, why is it there? So to explain that, you need to invent.
Okay.
Right? So part of it is discovery. But to explain the discovery, you might have to come with new techniques. And you don't come, mathematics really, you see a pattern emerging, but then you want to explain why is there this pattern. And in order to explain that, you come up with inventions. And these typically turn out to be techniques or tools which eventually end up having applications in so many other areas, both within mathematics and also outside of mathematics. Right? Let's take the simplest case again, prime numbers. So prime numbers exist, right? If you grant numbers exist, in the sense, once humanity discovered 1, 2, 3, 4, and then the properties of multiplication, addition, divisibility and all that, then it's eventually they'll stumble across prime numbers. So that's a discovery. But then again, you discover that there are infinitely many prime numbers. But you want to understand, okay, there are infinitely many prime numbers, but how do I prove that a number is a prime number? In order to do that, you'll have to invent methods. That's not a discovery anymore. Right? Or as you go farther and farther, you want to measure the distances between prime numbers. Or you want to count, let's say, how many prime numbers there are less than a given real number. Right? And in order to develop that, or in order to understand, give a full understanding of that, then that leads to inventions. You have to come up with techniques which have to be validated by other mathematicians. You might guess along the way, okay, the next prime number is going to be this much farther away. But then you have to explain why that is so. And in order to do that, you'll have to invent techniques.
It's like finding a forest, but then to get to know more about the forest, you have to navigate through it.
Yeah. Right.
So ma'am, you talked about what drives mathematicians when you were speaking about your initial field, and you said that they don't do it just because to explain something or because it has got some use. It is the curiosity that drives them. Starting from young kids, how does one get fascinated by mathematics, and what is it that at specific points keeps it going? It cannot just be curiosity.
Well, I would say part of it has to be curiosity, but part of it has to be this sense of mystery, right? I mean, like, let's take the number pi, for instance. Kids can do this experiment. Draw any circle, measure the radius or the diameter, take the ratio. And it's always the same. Now, why should it be the same? You want to understand why it's... Some people might say, okay, why I don't care. But then I think children, if they are curious and if they get interested, they'll draw more circles, they'll measure more diameters. And then it's really fascinating, right? I mean, the smallest circle or the largest circle. And then you explain to the kids that, this is how people discovered, and then it led to astronomy, and then tell them stories about how using such mathematical concepts, much before anything fancy came up, people could come up with the radius of the earth or the distance from the earth to the moon. You didn't need a telescope. All this was done with pure thought. And another example I like to give, I always like to say that when you compare mathematics with other subjects, let's say physics or biology, gene was maybe 100 years old, 100 odd years old, but already finds its way into the textbooks. Now, I'm not sure how many children actually know what a gene is or what it do, but it still becomes kind of cool to talk about genetics. I want to do genetics. I want to do criminology using genetics and so on, right? How much do they understand about the actual DNA? It again becomes words that you can throw around. Or similarly in physics, you can say, I want to understand the universe, cosmology, string theory, black holes, blah, blah, blah. Now, mathematics, that's always the problem, that the distance from what is known to when it finds its way to, let's say, school textbooks and so on, that's probably the longest. And that's because of the very nature of the subjects. You can't fool around by just throwing big words and so on, because whatever you have to say, you have to prove.
So, ma'am, as you were talking about the need and actually the beautiful part of mathematics is the abstraction that comes along. But when we are students, how we understand math is numbers. We count apples and we count melons, and that's how we start. But slowly, okay, there were numbers, and then there are operations. You're adding numbers. That is still very intuitive because you see that in everyday life. But after some point, abstraction is introduced to the whole thing, and suddenly there are complex numbers. I mean, day one, you were told that the negative numbers will never have a square root. That's just impossible. And after 2-3 years, you see that there is under root -1, and suddenly you're baffled.
No, you should. I think the right way again to say is, you look where negative numbers don't have a square root in the realm of numbers that you know.
Yes, sir. So that's one idea that you're not aware of as you're a kid, that this is like what we think is this is the entire space, and these are just the numbers that we will talk about. So where do you think at the student level, the first level of abstraction comes in, and why the abstraction is necessary?
For a very long time, you postpone the abstraction, right? I think up to 4th standard, not even in 4th standard. I think when do you learn negative into negative is positive? There's some standard, I think. Yeah, and there you say that as an axiom. And again, you can give a proof which a child studying in fourth or fifth standard, if you introduce a notion of direction, what is, after all, what is the sign? It's just giving a direction to a number. But this is already given the numeracy levels, and given that only certain kids might have an inclination for abstraction. So it becomes difficult, right? So that's why you have these axioms. You say, okay, take it for granted. And then that again becomes a point of contention for the children, because so far you have told them that mathematics, everything rests on proof. You have to, 2 plus 2 is always 4. It can never be that. And then suddenly you're telling them, okay, take this for granted. At the same time, it can be said, and unfortunately, I'm not such an expert in pedagogy, but I think already at that time, you should introduce the idea to the children that, this can be proved, except the proof is probably, it's not worth your understanding. It's like telling a child, another example I like to give, you don't tell a child that don't speak unless you can speak with perfect grammar, right? A child learns to speak, and then along the way picks up the grammar and then gets autocorrects and so on. So how do we incorporate that into the teaching of mathematics? So because if you tell a child, we won't teach you multiplication unless you understand the logic behind multiplication, right? So first you learn the tools, then later on, once you understand more, then you see, okay, why you're doing what you're doing is correct.
I think you already mentioned this, but in a more elaborate sense, what would your alternate pedagogical idea would be about teaching a kid mathematics and subtly introducing them to abstraction? What do you think would be the right level to start with?
I think you should start already with class 4, but also get them to do a lot of things by hand, So for instance, it's just not just numbers. It's also, you can do a lot of geometry, you can do angles, just get them familiar, with measuring distance. And then already they discover, fourth standard, they already understand that multiplication is nothing but repeated addition. But this is true only when you're working with positive numbers. And they still haven't seen negative numbers in that sense. So I think now the textbooks already in fourth standard, they see the number line. So get them to work a little more. You can come up with a lot of ideas for them to play with the number line. In terms of adding is moving in one direction, subtraction is moving in other direction. Then how do you think now doing multiplication on the number line already becomes complicated? So I would rather just tell them, I prefer the old method. Learn your tables. Right, and make the whole class. And this is actually, I find it, I don't know why people want to say that, sometimes we are throwing the baby out with the bathwater when we say you shouldn't learn things by rote. Learning multiplication tables or learning some of the things by rote, now people are discovering, after throwing the baby out of the bathwater, they are discovering that it's actually good to memorize certain things. Yes. And there is something nice when all the kids sit together, just like singing a nursery rhyme or something, singing the tables together. This can be a group activity, and at the same time come up with other. And today there is enough pedagogy, both in India and elsewhere, but again, implementing it in the classroom, because teachers are all the time focusing on completing the portion. So, and I would say spend more time on all this. And today you also have technological tools. You can give the child a tablet where they just keep practicing and then they figure it out.
Moving on to patterns and say series and structures that we see around, we see a lot of different these things, and I think I personally was very fascinated by numerical series and geometrical patterns. So the question I have here is, why is it that, say, our fascination or obsession with these patterns and structures, we find somewhere in the we find it almost everywhere, right? Like we find various uses to it. We find it being able to explain a lot of different things. And a follow-up to that would be like, do we sometimes overdo it? Like, do we sometimes try to look for patterns where there may not be any? Like, for example, prime numbers.
Right. Well, patterns, I think I think the human mind likes order, right? I mean, it can get used to chaos. but it's comfortable with order. And then also I feel it's somehow wired to recognizing quote unquote beauty, though what is beauty is can be debated and so on. But this somehow feeds into that. And you don't always look, yeah, you have to grant that there might not be patterns. But again, let's go back to an example. For instance, when rational numbers, the Greeks were very good with numbers. Early 3000 years back, they used to do a lot of number theory. But then they had to confront negative numbers, and zero was already hard enough for them. And then they came to rational numbers, which, if you're talking about patterns, you know that one way to explain rational numbers are those that when you carry out a decimal expansion, then there is a pattern in the digits that come after the decimal point. You might see the pattern only after million digits. But they also discovered that there can be numbers where this pattern doesn't exist. Those are the irrational numbers. And there's a story, it might be apocryphal, but there's a story that they were not allowed to speak about irrational numbers because they thought that it would disrupt order in society. There's a story about about when they were coming back on a boat ride, I forget who it was, some school, Aristotle school or somebody's school. One of them accidentally blurted out about the discovery of irrational numbers, and the others promptly pushed him into the sea because he was seen as a disruptor of society. What is fascinating is in many other civilizations, I'm sure the Mesopotamian civilization, the Chinese, Indians, they also had this intuition about irrational numbers. The Indians definitely, we know that they had. For instance, in constructing the altars for the yajnas and all that, they had to come up because it had to be precise because they were making oblations to the gods. So everything had to be precise. So if you take a right angle triangle, they had to carry out measurements of the hypotenuse. And if you take a right angle triangle of 1 unit length, base and height, then the diagonal has length square root of 2, which is an irrational number. But to the credit of the ancient Indians, they said, okay, we don't understand this, but there are a lot of things we don't understand. And this is one of them. And then it becomes this question of, being open to mystery. And I think, I don't know, this is something very personal. I feel that part of the human mind is also geared towards looking for mystery. Today, the mystery has taken different forms. The mystery today, unfortunately, has taken the form of interest in TikTok videos or interest in this misinformation, things of that kind. But there is a part of the human mind which is drawn towards mystery. Why do children get so drawn by magic?
Yeah.
And part of mathematics is trying to come to grips with this mystery, being fascinated by mystery and trying to come to grips with that mystery.
So, how I understand the obsession with patterns and series is that we have discovered something very large, say a very big forest, and we do not know everything about it, and maybe the human brain can't comprehend everything at a time. So we try to look for parts of it in different perspectives. It's like the Plato's shadow cave allegory. An allegory of a cave. So we try to select different progressions, structures, series, and then we have like 1,000 different snapshots or projections or shadows of the whole big thing, and then we try to put it all together to be able to understand.
That's a very good analogy. Yes.
Okay, so one thing that I have noticed in my own personal experiences is that the mathematics that we learn till 12th standard, let's say, and the mathematics that goes on in the higher level, which is basically people do in their PhDs or master's level, is quite disjoint in some manner. I mean, there are terms that you've not heard till 12th standard, and which you hear, okay, who's working in mathematics? If you just talk to them for like 5 minutes and they'll explain, so I'm working with on group theory and there are these numbers, and this is just like the most basic terms I'm putting out that I am aware of. And you get a sort of overwhelmed by it because when you talk about physics or you talk about biology or chemistry, there's always this, okay, so you had learned this at a basic level, now I'm doing the same thing at a higher level. But in mathematics, it seems quite disjoint. So do you think, is it because of how the course structure is constructed, or where does it get so complicated? At what point did it become so non-intuitive?
Now, this might sound a little biased, but I think it's because of the richness of the subject. And also, I mean, look, this again comes back to what I was saying before. Like you dig a little deeper when somebody says, I want to do physics, I want to be a cosmologist. Then ask them, okay, what does it mean to be a cosmologist? So we are only familiar with this word cosmos. Then cosmology becomes a study of the cosmos, study of the universe. So these phrases you understand. But the same physicist can actually, or string theory. Yeah, I don't know, it's not so sexy now, it's not so fashionable now, but a few years back, it used to be very fashionable. But nobody tells you that whatever understanding the physicists have of string theory, it would not have been possible without the mathematical tools that were already developed. And for me, this is a classic example of the richness of the subject, and you cannot explain the tools, right? It's like an expert, an expert who's working with, let's say, high precision tools and so on. It all looks very fancy, but you know that you require a lot of training to use the same tool. Whereas somebody else is using the tool to make that beautiful thing, and you only see that beautiful object, not appreciating the kind of tools and the effort that went into making that.
I mean, at some point, I think this abstraction also scares people off, like the mathematics and the richness, as you say it. It also becomes, I mean, it's basically like something is so beautiful out there that you're all actually scared of addressing it because you might not be able to perceive it entirely in some sense.
And again, for this, there should be more pedagogical thought going into this about how do you separate the people, the students who are interested in abstraction, to lead them more on those lines, and the others who are not interested. For instance, many people ask me, what's the use of complex numbers? Or many students don't even know what's the use of logarithms.
Yeah.
Right? But to tell them this simple fact, look, logarithms, is it easier to multiply or to add? Addition, everybody will agree that it's addition. And logarithm is just a tool to convert multiplication to addition, especially before the invention of the computers and so on. Right? And similarly with complex numbers, but that's exactly the point, I mean, complex numbers are used everywhere, but even to communicate how they are used, that calls, and that's part of our pedagogical system, we need science communicators or math communicators who can break it down. Mathematicians, and this rift has been going on for too long, where a mathematician is somehow, you're doing your mathematics, it's never important to communicate what you're doing, right? But today people realize the importance of that. And how do you train? And it again, that calls for a different amount of training. I might not be interested, or I might be interested in getting trained as a math communicator. So we should devise courses for that. And that should become an integral part of learning science. And that's where technology is again helpful. Just imagine at the end of complex numbers, you have a few short presentations or videos saying why without complex numbers, your latest luxury car would be impossible. Now, they might not understand. To actually give the details of that might call for deeper mathematics. But somehow just making that connection makes the student realize that, oh, okay, I'm not learning something that's totally useless. Or equations, solving equations, logarithms, all of that. Just tell them, since you're all from Space University, a rocket will not go up into space without mathematics, without equations. Right? Immediately it changes the way they approach the subject. And then you can say, all right, now do you want to understand why without complex numbers, rocket can't go up? Then make a small presentation about that. Right? So all this calls for outreach and communication, which is slightly different than the actual study of mathematics.
Idea of abstraction and having different ways and techniques with numbers, we have now even extended it to geometry. Maybe it started a few thousand years ago, but now in recent times we have extended it quite a lot, I would say very extensively, to geometry. So would you like to talk about a little bit of algebraic geometry and what it involves?
Algebraic geometry is perhaps a little too abstract and will get technical, but it starts with the study of solutions of equations. And you want to give it more structure. Like if you take just the integers, you know that it's not just a set. It's not just 1, 2, 3, 0 and -1, -2. It has these other rules that it follows. When you add two of the elements, you're again within that set. You don't escape out of that set. And then for every element, there are these two special elements, 0 and 1, such that 0, you have the negative, which when you add a number to its negative, you get the special element 0. And then there is 1, which you take any number, multiply it by 1, you don't change that number. Now, these can be abstracted, and then you can say, what other numbers, what other systems are there? What other sets are there where I can give these structures? And when you look at solutions of equations, you lose that structure. If you add two solutions of an equation, it's not, we know that even in the simplest case, it's not a solution. But you take groups of equations or, special parts of algebraic geometry, you actually learn that there are these special objects which which arise as solutions to equations. But then they have this remarkable property that if you add two of them, except the addition becomes totally different. It's not just the usual addition. Your addition, the way you add, becomes something totally different, where it involves geometry. Right? So, and again, it's remarkable how people discovered these, right? And but let me talk a little more about other aspects of geometry. Like, for instance, today there's hyperbolic geometry, there's Riemannian geometry, and so on. So just think of this. Just think of shapes. For instance, take a sphere. A sphere has no hole. Or you take a torus, which is like the vada, which has one hole. Or you can make a vada donut with two holes. How do you give this a mathematical meaning? And that's what topologists or mathematicians discovered, a few centuries back. Or this notion of curvature. When you're looking at the plane, just the plane, then you know that the shortest distance between 2 points is a straight line. But the same thing is not true when you take a sphere, right? There's no straight line. It's the longitude, the geodesic. And then this becomes an abstraction. If I take any, and then this is something people can relate to. You have different shapes. And then you take 2 points on any three-dimensional object. How do you define the shortest distance between them? Then you are forced to deal with curvature. And then how do you give a mathematical meaning to curvature? And again, here we come back to this notion of how mathematicians did all this out of pure interest or pure abstraction. But today, when you talk of space-time and gravitation being heavy mass causing a curvature in space-time, they have to come back to those mathematical terminology and precise notions which were developed by mathematicians, right? So this is Riemannian geometry. No, another example, this is an example I like to tell my undergraduate students. When students are learning matrices, for instance, they don't understand, why are we doing all these things? Why are you putting a set of things inside that? But your Google search today would not be possible without matrices and all the abstract concepts that were developed with matrices. And, the person who actually did this, Grassmann, he was a German mathematician. When he did this, I forget the exact time, 18th or 19th century, when he started studying matrices and so on. Even Germany, which was quite advanced in mathematics at that time, even the pure mathematicians at that time felt it was too abstract and didn't see it going anywhere. And in fact, there's a story that Grassmann got so dejected that he gave up mathematics and moved to, I think, Indology or languages and so on. And today, 250 years later, you realize that whatever he did with matrices has so many applications, in probability, in statistics, and more importantly, in Google search. But again, telling the students how this is important, it's going to be, and that's where, again, this notion of people breaking down and saying, okay, let me explain to you in simple words how matrices play a role in Google search. Those can be part of school projects or, again, don't force it, but to the curious or to the students who are interested, make it available. And again, that's where technology comes in. Today you have, there's an information overload, but you can have mentors who can guide an interested student to actually go deeper and discover these things, which hopefully will spark further interest and so on.
And ma'am, while we're trying to understand ways of understanding mathematics, basically, there are so we started understanding something with equations. Now those equations were put onto a graph and you could visualize it. You could see a figure out of it. You could solve it in that manner. So it's always been sort of a pattern, and I would like your ideas on this particular notion that there's always been that while we're trying to explain something with conventional ways in mathematics, we've come to a limit. And that's when we've generated a whole new set of world of explaining that particular, a new way of formulating the mathematics that we're looking at. For example, how Feynman used the diagrammatic ways of problem solving and explaining things. So because we're limited by the conventional methods. So, what are your ideas on this at the number of ways mathematics can be formulated? And it's quite fascinating in a lot of ways with you.
Yeah, but it's again individual taste, right? Like some students might be good at geometry, and they might have a geometric intuition and might want to apply the geometric intuition. But some of them might just be comfortable with abstraction and not be afraid of abstraction. So we should find different, and again, keep coming back to this. All this is possible today with the technological tools that we have. But it calls for a different approach to learning. It calls for a different, involvement of pedagogical tools, in involvement, and again, to find somebody who's in pedagogy who can appreciate these nuances in mathematics, or a mathematician who can connect with the tools in pedagogy. So these are all trainings, internal trainings that have to happen. Like in UBC right now, we are doing an experiment where within the mathematics department, there's one course which is called, where there's history of mathematics, but there's also some course called mathematics and everyday life, where the teachers are encouraged to come up with ideas of what can be the syllabus and how it can be taught. And this is something that we will learn along the way. We will find that, okay, we wanted to teach this, but it just didn't work. But then you change track, and then you improve, you record it, and then get student feedback. What did they enjoy, and so on. Again, it's not clear that in a class of 120, all of them will enjoy the way it was taught, but there may be 10 students who have enjoyed. And so this is again something we have to get out of our thinking of, expecting everybody to be comfortable in everything that is taught. So they're just like there should be flexibility in teaching, there should also be flexibility in, or the other way around. There should be flexibility in learning as well as teaching.
Yeah. Well, I mean, do you think that there needs to be a shift in how mathematics as a subject is perceived? Like the mentality that people have towards it in general, I mean.
Definitely. And I mean, I've been saying that, right? First of all, it should be communicated to them over and over again that mathematics is important, that half of physics or physics Nobel Prize, for instance, again, I'd like to give this example of the Higgs boson. How many people actually know that there is a considerable amount of mathematics to that? Right? So just communicating this. I read a very fascinating, I don't remember if it was an essay or an interview. This is slightly different than mathematics. This is more about gender in science. So there was a student, she wrote she said she's a physicist, but she later wrote a book on Noether. And then she said, I discovered, Noether's theorem, it's called the most beautiful theorem, and so on. But how many know that it's actually a woman? And she said, when I was doing physics, it would have altered the way I did physics if I had known that she was a woman. Right? Because Noether, there's also her father and brother. But it was this Noether who's really the strongest of all three. And she says it would have changed my whole mental approach to what I was studying if I had known that there was a woman who did such great work. So similarly, if somebody knows that mathematics underlines so much of knowledge, it might change the way they engage with the subject.
I mean, and this goes in hand with the fact that mathematics is so universal. I mean, it's literally everywhere, and yet, it seems like something intimidating to people.
So, ma'am, oftentimes in mathematics or even in other fields, we come across a new problem which we do not have the tools to deal with, or maybe the way to approach the problem, it would not click. And very often we resort to maybe trial and errors. I think maybe it is the most used method till now to explore these new things. So do you have any personal anecdotes or personal experience with this sort of a thing where you were stuck with a problem at a point and you
Yeah.
tried
I
to
mean,
brute force your way out of it?
yeah, no, I think again, speaking from my personal point of view, in the larger scheme of things in mathematics, like I said, there are conjectures, right? You have an intuition that something should be right, and then you call it conjecture, and sometimes conjectures become so famous that even somebody who disproves the conjecture can get a Fields Medal because nobody has been able to disprove the conjecture for a long time. So people believe that it's true, but when somebody disproves it, it's equally interesting. And also when somebody proves it, it's equally interesting. And of course, the most famous one out there is the BSD. I don't know if you've all heard of the BSD conjecture, Birch Swinnerton and Dyer conjecture. It predicts a connection between two totally different things, one which is completely algebraic in nature and one which is completely analytic in nature. Now, how was this conjecture formulated? This was formulated in the 60s when the computers had just come about. And Birch and Swinnerton Dyer, these two mathematicians in Cambridge, had an intuition that there must be this connection. And they ran various numerical examples on the computer. And they got a lot of data, which made them believe that they were on the right track. Now, this conjecture is still open. But there are, an arbitrarily large number of cases where you know that this conjecture is correct. In concrete examples, you know that this is correct. But mathematics is not happy with proving it for n arbitrarily large. You want to prove a statement in general. Now, that is still open. But given any object, given any concrete object, you can test it and see that it's correct. Now, along the way, now as computers have become more and more powerful, there's this whole computational number theory which is coming along, where on the one hand, you have this very deep mathematical objects, but on the other hand, there is a computational aspect to them which you can compute. So once you have a certain intuition, you can test out your intuition by actually doing computations, which would have been impossible without the computers. And along the way, when you do these computations for large numbers or large values, then you see that there is a pattern, right? There's something happening, like something is vanishing when some other phenomenon is happening. And then that feeds into theory. So that becomes a question for a mathematician. Why is there this pattern? Then you come up with more theories for why this pattern occurs, or this gives you a problem actually to say, okay, this phenomenon happens under these conditions. And then you prove it in abstraction. You haven't solved your original problem, but you have unearthed new phenomena which is connected to the original problem, which would have been impossible without the data, without the actual computations. So that's a new, very interesting, aspect of mathematics now, these computational aspects, which you can do concretely, both in algebraic geometry, in number theory, and so on.
Like we've already discussed through the session, that pure mathematics isn't something that we can see on the onset at how it's affecting the world and all of that. So do you think, is there an effect on the community or the number of people pursuing pure mathematics because of the trends of the profit-oriented view that individuals have right now? Do you think that the number of people pursuing pure mathematics is reducing, or the drive for it is reducing?
It's not just pure mathematics, it's pure science in general. I read it was quite sad to read recently that many of the universities or colleges are closing down their science departments. And somehow this message hasn't gone from the highest level, from the policy makers down to families, that computers would not have been possible, or technological advancements would not be possible without theoretical advancements. Right? Your MRI would not have been possible without all the understanding in physics and mathematics on imaging. Right? And, there should be, again, there was some progress, like people were encouraged to study pure science because in between in India, this whole move towards IT and electronics. So at that time, there were various scholarships which were instituted for students who were interested in pure science to stick to pure science. But I think here industry also has to take a lead. So for instance, in UK, in Europe, and in North America, I teach many students who, they would be actors or musicians. They might be pursuing a degree in music or in business, but they will sit in my linear algebra course or in my calculus course. It's torture for them as well as for me, but it's a modern rite of passage. Why? Because the industry and society, from banks to insurance companies to other industries have understood that if you're trained as a mathematician, then you're trained to think logically and you can be trained to do anything else. Whereas unfortunately in India, at least this was my impression. I've been away from India now for, I don't have that much connection to the ground. But when I had a decade ago, in India, I noticed that the perception was different, both in industry and in the real world. If you were an academic or if you were interested or if you did in a PhD, you lived in an outer world and they were not sure that you would fit in the real world. Whereas I've had students, PhD students, postdocs, who say that after reading a mathematical paper, which is 25 pages long, it is trivial for me to read 100 pages of financial mathematics or anything related to finance. So this message has not sunk in India.
This was a conversation from the 4th season of Zeroing In, the Science Podcast, where we're exploring the richness of the mathematical world and the ideas that make it the language of the universe. We extend our sincerest gratitude to Professor Sujatha Ramdorai for this lovely discussion on behalf of the Zeroing In team for this episode, which included the season team, and my co-host for the session, Fenil Shah, and I am Shreya Mishra. Thanks a lot for listening to this episode. We'll be back soon with further interesting questions and conversation with eminent Indian scientists from across the world. If you have any suggestions, you can visit us on zeroingin.org or write to us on zeroinginpodcast@gmail.com and follow us on our Instagram or Facebook handles @zeroinginpodcast for the latest updates.